Third and last day of our workshop. Today the focus changes somewhat to more the gas dynamics and MHD of protoplanetary disks, starting with Mark Wardle on magnetic activity in protoplanetary disks.
Whatever they're called.
Whatever they're proto-something.
Okay, thanks. So I've got a snapshot here from yesterday evening's banquet, which might explain the somewhat depleted numbers. But this is kind of the feeling I've got at the moment from attending this program and the workshop and so on. We're trying to deal with something that's very, very complicated, and it's quite confusing to understand. So the approach I'm taking in this talk is to try and give really an overview that will provide some context for some of the talks that will follow on about MRI and magnetic stuff in disks. Of course, this isn't just my own work. I've got a list of collaborators in strict alphabetical order of last name. So Catherine Brading is here. She's a PhD student. Raquel Salmeron is kicking around somewhere. There you are, Raquel. She's attending the workshop. In addition, Aria Kernagel is involved at Chicago, and I have a postdoc, Pandy, back at Macquarie, sending me drafts of papers I'm not responding to quick enough. So really the role of magnetic fields isn't that clear. We have these theoretical ideas and probably prejudices, and we have precious few observations that tell us really what's going on. And that's a problem because we think magnetic fields are very important. They're a pretty efficient way of transporting angular momentum, whether you do that through MRI turbulence or you do it with some kind of centrifugally driven Blandford and Payne type wind. Various ideas have been tossed around through the ages: dynamos, coronal activity, and so on. So I've cheekily drawn a protostellar disk here with net flux through it. Because that's a fairly natural configuration that you get from the gravitational collapse of a molecular cloud core, but that of course could just be theoretical prejudice speaking again. The strength of the magnetic field, we don't have any direct measurements. In the densest part of cloud cores and shocks and so on, you see OH masers, you get 10 milligauss field strengths. The magnetic field in disks, at least initially, is going to be at least that, and probably much more because of compression and winding up of the magnetic field. If you take the minimum mass solar nebula and ask what the equipartition field is at the midplane, you get about 18 Gauss at an AU. Of course, you could have 10 or 30 times the minimum mass solar nebula, and this maximum could go up. There is some evidence, or there was some evidence, meteoritic evidence for Gauss-like fields, but there's also the possibility that these are dynamo generated now, so that makes things muddier again. But if you want to invoke magnetic fields to transport angular momentum, you do need a Gauss to get the accretion rates that we need. And the estimate is very simple. He says reach in for the big stick. So if you write down the momentum equation and pretend things are steady and axisymmetric, then you're left with, you take the phi component, so you're talking about angular momentum, and you can either transport angular momentum through BR, B phi stresses within the disk, or BZ, B phi stresses, taking things vertically out through a disk wind, for example, or magnetic braking. And then to make an estimate, you can assume that you've got Keplerian rotation, and use div B as 0 to tidy up the magnetic terms, and then start making estimates just by integrating vertically at a particular radius. So the rho VR turns into m dot. You get BZ, B phi torque applied to the disk surface because of magnetic braking, if that's there, and you get some kind of average BR, B phi stress if you're thinking of some kind of turbulence within the disk. And notice that there's a factor of h over r lack of efficiency in the transporting things radially case. So if you take the best case, the most efficient case, where you remove things vertically through magnetic braking and work out an estimate for typical accretion rates of 10 to the minus 7 solar masses per year at later stages, you get a field strength of order 0.2 Gauss. H over R is around 30, say, at 1 AU. Take the square root of that, you pick up another factor of 5 or so. And then the pluses and minuses and the turbulence might give you another factor of 2 or something like that. Whatever you do, you end up with somewhere in the range of 0.2 to a couple of Gauss, typically for that typical accretion rate. So that's a fairly general argument. So that gives you some idea of the field strengths we'd like to have if the magnetic field is doing the angular momentum transport. Now, every time I show this flipping cartoon, but it's an important point, of course, that disks are very poorly conducting. And we have very high magnetic diffusivity in them, which is good in some ways and bad in others if the diffusivity is too high. So we have very high density. We have external sources of ionization, X-rays, maybe cosmic rays, probably not. They're probably excluded from getting in, which can penetrate only so far. And then you have to rely, if temperatures are cold, on kind of radioactive decay or thermal ionization closer in when the temperature gets up to around 1,000 Kelvin. So you have this very strong, you have this radial structure and strong vertical stratification in what's going on with ionization and the gas density, and that affects how magnetic diffusion works. And when diffusion is high, you expect magnetic activity to largely disappear and create dead zones. So this diffusion is really essential for any reasonable theory of what magnetic fields are doing in these disks, one way or another. And the type of diffusivity I'm talking about here is not anomalous. This is just collisions of charged particles with neutrals with well-determined cross-sections. So you can't fudge those numbers. So you're stuck with the numbers that nature gives you in some sense. So we might like this or that, but actually nature will determine what those diffusivities are, whether we like it or not. And this is important for all kinds of things. You know, you have some turbulent cascade maybe. Where does that dissipate? If you're trying to accelerate an outflow, you've got to have material filtering in here. Some material ends up attached to field lines and flung out. Diffusivity is an important part of that problem, and so on. And there are these multiple diffusion regimes because we have a gas that's a mixture of neutral particles, ions, electrons, and charged dust grains threaded by a magnetic field. And depending on, there's two different ways of looking at it. One is thinking about frequencies and going to higher and higher frequency. The other is thinking about going to higher and higher density. I guess I prefer actually to do it in terms of density, even though I've got frequency there. So at low densities, the magnetic field and ions and electrons can drift freely through the neutrals. There are collisions, but they're not sufficient to decouple the charged particles from the magnetic field. So the flux is still frozen into the charged component of the gas, and all that drifts together through the neutrals. That's amber polar diffusion. That's most important at low densities. There's an intermediate regime, the Hall regime, where ions become decoupled from the magnetic field and electrons do not, because ions have a higher mass, so it's harder for them to keep coupled to the magnetic field, and the collision cross-section is also somewhat higher with the neutrals. So at intermediate densities, the magnetic field and electrons can drift through the neutrals and the ions can be tied to the neutrals. Right, that doesn't give you charge separation, don't worry about that, we're doing MHD, but it changes how the magnetic field drifts through the gas. Finally, if you have enough density, then all charged particles are decoupled from the magnetic field and you're in the resistive regime. So it's quite easy to generalize MHD to include this. This is by no means the first attempt to do this. You end up with multiple diffusion coefficients. You've got ohmic resistivity, a Hall diffusivity here, and amber polar diffusivity. And you have this nasty curl of the electric field sitting here, the electric field in the frame of the neutrals. And it's kind of interesting to write it in a slightly different way. You can write this which gives you an idea of flux transport. So this VB is the drift of the magnetic field with respect to the neutral gas. And that incorporates the effects of amber polar, ohmic, and Hall diffusion. And then there's this leftover term, which is the nasty ohmic bit, which lets you reconnect field lines and destroy flux by cancellation and that kind of thing. Everything else just moves field lines around. And then if you look at dissipation, the Hall term doesn't give you any dissipation because the associated currents are perpendicular to the electric field in the frame of the neutral. So there's no dissipation, which is kind of weird and sometimes dangerous. Now, the critical parameter that comes in determining which of these regimes is really just the ratio of the magnetic field to the density, because the magnetic field strength controls how strong the Lorentz forces are on the charged particles, and the neutral density determines how severe the collisions with neutrals are. So the ratio B over N is what's important. And so if you think about a plane consisting of log B on the y-axis and log N on the x-axis, lines of constant B over N are important. In the high-density regime, you've got normal resistive MHD, there's an intermediate Hall regime, and then there's the ambipolar regime for relatively high field strengths or low densities. So if you map now the midplane of the minimum mass solar nebula with the equipartition field, you get a line through this. These red lines tell you when ions and then electrons become decoupled from the neutral. So the Hall regime is in here. So you can see, you know, at the midplane, you're somewhere along this black line, so you can go from the Hall to ambipolar, maybe to resistive. In addition, charged grains, this is 50 angstrom, 2500 angstroms, so that's 0.2 microns, millimeter would be over here somewhere, are very strongly coupled to the neutral gas and don't drift at all effectively. So I'll come back to that. But diffusion is important in ideas about gravitational collapse and magnetic braking and so on. And I think when I was a lad, we thought we understood what was going on with magnetic braking and getting rid of flux. You know, ambipolar diffusion was going to get rid of flux in cores and let them collapse. The problem now is you can bring in a lot of flux during the collapse, maybe too much, and it can be hard to get rid of. In addition, magnetic braking is so efficient that you can fail to form a disk. So, you know, diffusion weakens that, but I don't think we've got a good convincing calculation that tells us that everything's okay with both those issues. So this is just a recent 2D simulation by Mellon and Lee, just for something nice to look at. These contours are density contours, and they're flattened here, not because of rotation, just because of the effect of magnetic stresses. So this is not rotationally supported, this structure. There's no disk in this simulation. Though other simulations do form disks and other calculations. This has led, for example, Frank Xu and his co-workers to propose models where when you form a disk, it's fairly heavily magnetized, magnetic braking is severe, and the disk structure is only 70% Keplerian as stuff spirals into the midplane. I'm showing this plot just to show you, of course, Frank explains everything, so there's many curves on here, but T Tauri stars, for example, are this black line, the magnetic field, and you see, of course, that at an AU you're getting actually a couple of Gauss in this model, so magnetic stresses are quite important. But you get the same ballpark figures because if you're trying to do something interesting with the magnetic field, that's what you need. And that's not a proof that everybody gets a couple of Gauss is not proof that it had to be a couple of Gauss. It's proof that everybody wants to get m dot of 10 to the minus 6, 10 to the minus 5 solar masses a year at 1 AU. Now, I want to talk a bit more about drifts because, you know, there's this whole thing, and I've stood up and raved a few times at different meetings, but it's good, I think, to try and give you a good idea of what difference does it really make in some kind of at a conceptual level. So here's a cross-section of a disk threaded by some flux. I've suppressed the azimuthal component, but let's imagine also the field is bending out of the plane of the screen here. Ignore these blue arrows, that's if you're doing a wind. But you're going to have this field geometry if you're driving a wind or you've just got magnetic braking operating. And now imagine that you look down vertically on the disk. So in this configuration, you see the magnetic field pointing at you. The J cross B stresses are tending to push things out radially and also backwards in azimuth because there's a torque slowing down the flow. And then in ambipolar diffusion, the drift is parallel to J cross B, just like it would be in the ohmic diffusion case, right? The field tends to try and straighten. Now, if I globally reverse the magnetic field by changing the direction of the arrows, that changes the current, but it doesn't change J cross B and the drift is exactly the same. Right, so this is kind of the standard kind of case we know and love. But now let's consider the limit of Hall diffusion. In that case, you're in a regime where the magnetic field and electrons can drift through the neutrals, which are now effectively carrying a positive charge density, the ions, so it can't drift through them. And so the drift of the magnetic field and the electrons is now opposite to the current by definition in this limit. Right? So I have the same magnetic configuration here, so I've got J cross B in the same direction, but now the drift is in a completely different direction. It's orthogonal to what it was before. And if I reverse the magnetic field globally, I reverse the direction of the current density, and so the drift reverses. Right, so it's this kind. So this is the fundamental difference: is that magnetic fields drift in a different direction. J cross B is just J cross B. It doesn't matter what diffusivity you've got in there, but the evolution of the field is quite different. Now, you might be mildly uncomfortable at the idea of the magnetic fields drifting inwards in radius faster than the neutrals. This is the drift with respect to the neutral gas. And there's some interesting things to think about there, but it's a real effect. Now, Catherine has been working away looking at the effects of this kind of thing on gravitational collapse. So she's managed to get some similarity solutions out. So what's plotted here is just surface density and magnetic field strength at some instant of time, 10 to the 4 years in this calculation. And this is for a Hall diffusivity that's 20% of amber polar diffusion. In the middle here, you've got a rotationally supported disk. Then there's kind of a shock as stuff comes into the disk and slams into it. And there's the analogous thing to an amber polar diffusion shock here, where the material comes in and the field is just sitting there and it slams into it. So there's some structure there, which I'm not going to talk about in detail. But if you compare this with the amber polar diffusion case, you can see that the inner disk changes radius by a factor of few at this instant of the calculation. And if you globally reverse the magnetic field, the disk is 10 times bigger than having the other orientation of the field at this instant. Now, this is a similarity solution, so if you come back in 100,000 years, everything's moved out by a factor of 10, because the similarity variable is r over sound speed time. And there's a power law of time that gets applied to the magnetic field strength and the column density. But this is illustrative of the potential this has to change the dynamics of collapse to form a disk and to affect things like magnetic braking. Okay, let's get to the magnetorotational instability, which I'll skim through pretty quickly because my time's starting to go. So this, of course, is this instability. This is the simplest case where you imagine a vertical field, you buckle it, and some fluid elements move in, others move out, and there's magnetic tension linking them. So it's like if you have two planetesimals on circular orbits, neighboring circular orbits, and you link them with a very weak spring, then the innermost planetesimal tends to spiral and the outermost spirals out. So the linear dynamics is accurately described by that kind of thing. So at least I've worked planetesimals into this talk, so I can relax. Now, so conceptually it's quite simple. So if you imagine looking down again on this magnetic field and thinking about a couple of these fluid elements, one moving in and one moving out. So let's say their initial position was here, and then I move one over here and one over here. The magnetic tension force associated with this buckling is going to be trying to pull things back, right? That's your weak spring effect. So it's like you've got two planetesimals here, and there's a weak spring here, right? And the star is over in this direction. This is radius. You've got these J cross B things. So for amber polar or ohmic diffusion, the magnetic field is going to try and slide through the neutrals in this direction. And that, of course, is trying to reduce the magnetic tension. So amber polar or ohmic diffusion tends to wipe this instability out if it's too severe. Now, if we look at, and if you reverse the magnetic field, again, the drift doesn't change, but the current does. So now I've got the field going into the board, and I've got the amber polar diffusion drift, which is, of course, anti-parallel to the current. It's not clear whether this is good or bad, because it's going orthogonal to J cross B. So whether it's good or bad depends on various competing geometric kind of processes. right? Because the field is not trying to go back necessarily to its original position. It's trying to head off sideways, and you think, well, this is going to stretch things more in phi, so that's one effect, but then this is tending to go back to its original radius, and so that is. So is it going to be good or bad? Well, the answer is it depends. And of course, you get different behavior if you reverse the sign of the field. So if you consider what kind of dispersion relation you get as a function of Hall and this pedism, this is just amber polar plus ohmic diffusivity, you get a space that looks like this. If you've got too much Hall diffusion when it's negative, you kill things dead. If you're over at the positive side, things are fairly normal. And then there's this place here where there's kind of dragons where zero wavelength modes grow, or are the fastest growing mode. But they're in a limited region of parameter space. And this is just maximum growth rate. So the normal things people think about are either ideal MHD right here, or resistive MHD, which is along this vertical line. But it's just part of this bigger picture. We know in protostellar disks we've got these mixture of diffusivities. So it's going to change field evolution, how the MRI works, wind launching, flux transport, and so on. Now, just to finish up, just to give you some kind of application of this, if you make a simple model of ionization at 1 AU and a minimum mass solar nebula, so here's the ionization rate, it's X-rays. I've included cosmic rays here to stop things just zeroing out here. And you've got electrons, metal ions, molecular ions, and some other light species. So it's a simple model, no grains. You can compute the diffusivities. This shows as a function of height above the midplane and the field strength. The color shading tells you what the dominant diffusivity is. So you've got ohmic, Hall, amber polar, and these boundaries are just where the respective ratios of B over N are just right to start decoupling electrons or ions. So you can see there's this big region where Hall diffusion is quite important. The contours are the magnitude of the most important diffusivity in log. So they're step by powers of 10. You can work out the local MRI growth rate at each position. So this is requiring a mode to fit in a scale height. So it's a very local calculation, so it's not quite appropriate, but it gives you a feel for things. And if you just take those ionization calculations and assume only ohmic resistivity, you get a dead zone and you get strong growth higher up. If you include amber polar diffusion, that adds more diffusion to the system that tends to damp things, and it reduces things a little bit. If you add Hall diffusion, in other words, include it because you shouldn't have neglected it, then that moves things around as well. Right, so I'll just bounce back once or twice there, just so you can see. Tends to, the Hall thing though depends on this. Right? If I reverse the sign of the magnetic field, it makes a big difference because if it's less than -2, it kills things. So, this is noise here, not zeros. So I'm not exactly sure of the exact boundary here, but it's around here somewhere. But that's kind of preliminary, this plot. But you have to watch out for that one. It's very easy to kill things, although usually I'm up here saying, look, it makes things grow because that's what we want. Actually, it's very effective at killing things.
Reverse it with respect to what? Like if it's upside down?
Oh, it's B dot omega in this limit that BZ is, B is parallel to omega. And the reason it comes in is because you've got this asymmetry in what electrons and ions are doing. That's what you need. So the fluid is not symmetric. And you can have the opposite sign be good if you bung all your electrons on grains, so they're the negatively charged species, and the ions are sufficiently coupled, then you can change which orientation of the field is important. Raquel has been calculating some disk wind solutions to show that you can launch a wind under these kind of conditions. So focus here on the Z component of velocity, so you've got a quasi-static disk, and then the wind gets launched through a sonic point. So there's the big issue for disk wind models is whether you can really launch things in a coherent way from a range of different radii. Finally, if you add grains, that changes the picture quite dramatically because the grains soak up electrons. Grains are like little footballs, they have a hard job drifting through the neutral, so you're reducing the mobility of charged species. So this is the similar ionization calculation, but now I've included single size 0.1 micron grains, 1% mass total compared to the gas mass. And these are the charge states, so they get reasonably highly charged because I've assumed the temperature is like outside 280-ish degrees. And there's kind of a critical place where the grains really start soaking up the electrons because there's a certain capacity the grains have to grab electrons. Electrons come in and stick. Eventually the grains are so negatively charged, not many electrons are able to stick because they don't have high enough speeds, and ions can come in and start neutralizing the charge. But eventually the electron density gets so low, the grains are not saturated in that sense, and that's really where this transition happens. And below this level, you have very high diffusivity and a dead zone effectively. Right, so here's the MRI growth rate. See, nothing happens near the midplane. If you make the grains bigger, they have less charge carrying capacity because you're hiding mass inside the grains so they can't grab things. So that helps. All right, so I should summarize what I've kind of said here. So firstly, we're talking Gauss strength fields at an AU. Whatever thing you want to do with them that's going to drive accretion, if that's what you want to do, that's what you need. Molecular cloud core collapse calculations, either coincidentally or by design, give B of this order, so maybe we should be thinking about net flux calculations all the time. That would be my bias, but that's my bias. There is this issue of magnetic braking. Could be too severe, so maybe you need to get rid of the field before then. And maybe you bring in too much magnetic flux into the center. Magnetic diffusion varies all over the place and does this weird thing with drift, so it can change things quite fundamentally. And we have this complicated issue with the grain population. So although in my models I can make the grains bigger, reduce their total ability to carry charge, that's good if you manage to do that by a factor of 1,000 or so, say, then you've got a fairly active 1 AU minimum mass solar nebula at 1 AU. But in any realistic model, there's going to be very small grains floating around which can carry even more charge per mass. And so you have to be quite careful in considering this. You need a very small, only a relatively small amount of mass in small grains can completely quench things. Okay, I'm going to finish there, I think. Thank you.
Fascinating talk, Mark. So it seems it's an intrinsically three-dimensional effect with the drift going perpendicular to J cross B. And so when many of us work with axisymmetric models, we have some intuition for the other two terms. The drift is parallel to J cross B.
Right.
Are we barking up the wrong tree with simplifications like axisymmetry? Like, do you need fully 3D to really?
No, you don't. To see this, you don't need fully 3D. I mean, poor old Catherine would be a long way off producing these plots if she was doing fully 3D. So what you need is to retain the phi components of things. You need, rotation. Even if you don't have if you have no rotation initially, you'll spin things up in one way and bend the field the other with the Hall effect, even if you have nothing. So you can't just set phi components of things to 0 and think they're going to stay 0. So you have to have rotation and you have to have b phi in there. But you can still get away with axisymmetry, thank heavens. Now, non-axisymmetry is a whole different, anything can happen in some sense. And really we need to do non-axisymmetric calculations all the time, right? But they're resource intensive.
More questions?
Mark, when you're considering X-rays, are you considering just the direct flux from the corona of the star, or is there some kind of scattering?
It's based on the IGEA and Glasgow calculations. Now, at the IAU, I was at the IAU in Rio, and Eric Feigelson gave a talk, and he mentioned that there's higher energy X-rays, 10 keV that they now know is there, and that will actually increase things.
That gives you better penetration, I guess.
That's right. So you're not, to order of magnitude, it's kind of the Thompson cross-section, which gives you the penetration, but that goes as 1 over E or something. Yeah, so that will give you better penetration.
So one might get thinner dead zones from.
Yes, that's right.
When you showed the effects of grain size, were you treating these as little spheres?
Yeah.
So what would happen if you started with some, They're very small grains, but you link them together into fractal-like chains and such.
I think that's a good question. At some level, I don't care because this is, having mono-sized spherical grains is a proxy for more complicated things. But nevertheless, when it comes to doing realistic calculations, these are important questions. So if you have fluffier grains, then you've got more surface area for a given mass, and that lets you catch charged particles more efficiently. Also, the carrying capacity of a grain, as long as the temperature is not too high, is only limited by the Coulomb repulsion of electrons by the grain itself. Again, if you have a stringy grain, then the effective radius, at least in some directions, is higher than for a spherical grain of the same mass. And that, in principle, would increase the charge that can stick. On the other hand, the grain is not as strong, and if you stick enough charges, you can probably explode it. But I haven't really looked at that kind of thing, because my attitude has been, well, we don't really know what the grain population is in terms of number as a function of time, so let's just do these toy calculations to get a feel for things. But it illustrates, I think, the potential complexity we have here with the feedback between dead zones and what the grains are doing. So it's it gets bigger than your head very rapidly.
I think we should move on and save some questions for discussion. Thanks, Mark.
Sure.